Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.
Several of the things that we look for when we actually select demonstrations for professors and talk to them ahead of class to try and pick out suitable experiments for them is, is it large enough? What particular principles does it demonstrate? We try and pick out experiments that are simple enough that there's only one or two principles involved, which is really pretty hard to do because even in the most simple of experiment, there's usually at least 5 or 6 things going on all at once. And so we wind up trying to emphasize the predominant principle in a given experiment. And we try and preview with the professor or the lecturer exactly how long each experiment will take to run. A lot of the critical things that we do when we're setting up an experiment is where we put it in the room. Sometimes that's nothing we can do about it. For instance, this big guy here runs on natural gas. So he's tied down to the bench in one place. A lot of the different experiments are mobile. They can be put in any place. Some experiments only work in certain areas. Some experiments, like optical experiments, only are visible when the light is forward scattered. So we have to place it in a corner where most everybody can see the optical effect. And we try and check whether the experiment is visible and try and make sure that it's not too cluttered. Well, all told, we violated almost every rule in our whole list. It's cluttered, it's messy. However, safety issues. We did put warning signs on everything. Well, a lot of this is stuff that you wouldn't think about unless you were actually setting it up. Voltage, everybody knows that. You don't want to touch high voltage stuff. When I came here, they actually had a DC power supply back here that supplied 300 volts DC, and it was just laying out on the bench. Well, we've done away with that because we like to keep our professors alive. Any magnetic field that's over 1,000 Gauss, we sign it. RF, well, you saw the sign. Anybody who has medical electronics has come down and talked with me ahead of the lecture because we have one device puts out huge amounts of RF, beam stops for laser emissions and other really bright, dangerous light type things. Vacuum, we put blast shields on. And other stuff's kind of obvious, just take care of problems. Our first really tough demonstration. This one's scary, the bowling ball. Let it go. Okay, nowadays you can actually buy a bowling ball that's bright colored, but we actually had to paint this one because this one's out of the 18th century, I think. And it's just a garage door spring. Now, this experiment is actually, believe it or not, used in our first term physics and our second term physics and even the third term physics because it demonstrates a principle that's universal, harmonic motion, where something that's set into oscillation with a number of restoring forces continues in that oscillation. And in fact, with something like this, you can stop it. Now you can excite this if I go at its resonant frequency by just wiggling the top of the spring a tiny bit. It's like pushing a swing set. And I've already exceeded it. It's bouncing the whole table now. We have actually had these clamps break, but most people know better than to put their foot under it. So you'll see this principle come up a little later. We need a strapping young man. You. Go over by Mark, he'll show you what to do. On this frame, we've got a set of pulleys, just a simple pulley system. And while Mark's showing him what he needs to do in a moment, we'll take a quick look at this. Everybody knows when you lift up on 100 pounds, you got 100 pounds. Don't we? Okay, we do.
Just say yes.
If you have a single pulley up there, well, you still wind up with 100 pounds. No big mystery. Okay, more complicated pulleys. If you have 100 pounds supported with 2 lines, well, it divides up 50 pounds. So you can kind of get that. It's pretty straightforward. More complex pulley, and this is kind of a enlarged version of this bottom pulley, showing what's happening with the lines. Kind of flips around like that. Divides it down by the number, so 25 pounds. So in essence, with a very simple pulley system, you can actually pick up immense amounts of weight. So we have a young fellow over here on our pulley system. Okay, give it a go.
Straight down.
Look at that, right off the ground. Thank you. Now that electric motor is actually over 400 pounds. And he found that no problem whatsoever to lift that up. And one of our basic mechanics demonstrations, but it's really nice because it's a real thing. You can show it, and it really does work. So we've got a long hollow tube, and on the top of the tube, which is pretty hard to see for most people, there's a series of 150, 200 holes. And we feed natural gas into one end, and we let the natural gas run for a considerable period of time until the tube fills up with 99% natural gas, because we want to avoid that natural gas fuel-air mixture thing. It causes problems with the demonstrations. So on the other end, we have a speaker, just a common speaker, but it's one with a plastic diaphragm, and it's sealed to this end so that the speaker cone is actually sealing this end of the tube. And hooked to the speaker, we've got a little signal generator, and that signal generator just produces a sound.
We usually have more gas pressure than this.
Well, we're able to see it. Okay, if you look closely, you'll see 1, 2, 3, 4, 5, 6 peaks. And if I increase the frequency, one, 2, 3, 4, 5, 6, 2, 4, 6. Our 7th one is right on the end here. 2, 4, 6, 8. There we go. Try not to drive everybody nuts with the sound. Everybody's seen a tuning fork. No big mystery. A lot of lecture halls use these, and how they use them I've never quite figured out. You strike this guy, and how many of you can hear that? Everybody can hear it, but it's not great. In fact, probably now it's very hard to hear. I can hear it. In fact, you're hearing a harmonic. The actual fundamental is almost impossible to hear. I can just barely hear it from here. Well, we have our demo lab tuning forks. Some of you may have seen these earlier. Now that's a real tuning fork. Now we've got a really nice thing. There's a lot of things you can actually show with a tuning fork. We're actually just going to show one thing. I'm going to set these 2 tuning forks. I don't know if y'all can see that. There we go. Everybody see that? We're going to set them about 1 inch apart, and I'm going to strike just one of them. This one on this side. Let him run for just a moment, then I'm going to turn him off. Okay, transferred energy. How? Through the air. And this is a property of a lot of different systems, and it's not only mechanical, but it transfers nicely into electromagnetic systems and many, many systems in our world. And we're going to run into this principle again. Whenever you have 2 systems that have harmonics or fundamentals at exactly the same frequency, if one is oscillating, it can transfer energy very easily into the other one, especially if they're coupled. And the coupling on this is actually through the air, and it's highly dependent on not only the direction, so if I went like this, it wouldn't couple very well, because these tines, you saw how I struck it on the end, they actually radiate off the ends a lot more than they radiate perpendicular. So many different systems use this principle, and we'll see this come up a little later when we get into some of our electromagnetics experiments. Our hoot tube, yes. Big cardboard tube. In fact, there's really, in fact, it's hollow, but there is a screen. I'll aim it around. Probably not everybody will be able to see, but there's a screen inside of it. And it's located kind of at a critical distance, but there's some variability. There's just a screen mesh in there. It's a heavy 1/4-inch grid screen. And go ahead, Mark. Okay, you killed the gas. Now that's loud, and it has no moving parts. Here, Mark. It's actually really loud up close. Thanks. Now, I've actually talked to a number of professors about exactly the details on how this operates, and there's no real close consensus on. So we won't really get into how it works, but it does work really quite well. And the main point that we're getting out of this, for the purposes of this lecture, is that the frequency that it actually puts out, that you're listening to, is highly dependent on the length of the tube and the diameter. So it's a tuned resonant circuit again. And much like this, where you can put a standing wave into it, that has its own fundamental standing wave. And it operates at that frequency even with no moving parts, with just a heat source inside of it. We're going to attempt to explode a wine glass. A lot of people have seen this experiment on TV, where at least some of the older people in the crowd, where the question is it Memorex or is it Ella Fitzgerald? Well, unfortunately, I don't have perfect pitch, nor is my voice particularly. No, I couldn't blow it up. However, this is a resonant circuit, a resonant structure. And if we were to drive this at exactly the frequency of a particular cup, we can drive it into its resonant state. I'll kind of start from the master oscillator. That's similar to this guy here that we used for the gas pipe. Just puts out a sine wave. That sine wave is fed to a power amplifier, and that's just nothing special. It's just a 100-watt Radio Shack special.
Right here.
That feeds into a horn driver. So this puts out a sound, and we tune that sound to the wine glass. And how we do that is the wine glass is sitting on a little piezo vibration detector, and whenever the glass resonates or moves, it couples that movement of the glass into an oscilloscope. The oscilloscope just allows us to look at what's going on as far as the vibrations in the cup go. And I call this a piezo vibration detector. Everybody has heard these devices. They're usually located inside of an electronic watch. When you hear that annoying beep, that's a piezo transducer. You can feed electricity into it, and it makes sound, it moves. Or if you move the piezo itself, it will produce electricity. It's a two-way street. So when the cup wiggles, it feeds through the piezo vibration detector. It shows up on our oscilloscope. One last thing is we have a strobe, which is, again, identical to the master oscillator. And the strobe feeds to a diode array over the top of the cup. There's our wine glass. And up in the corner, everybody should be able to see the oscilloscope pattern. So this is actually the pattern from our piezo detector right now. I'm going to turn it up to 1/10 of a watt, which isn't a lot. And everybody can see, hopefully, that sine wave now. And everyone should be able to hear it. Now I'm going to detune the cup right now. You'll notice the pitch of the frequency that I just changed didn't change much. The texture of it changed, though, because the cup is no longer resonated in tune with our driver. You also notice that the sine wave pretty much has gone erratic. Our trigger circuit isn't able to keep up. Now you'll notice that our strobe is now strobing the cup, and it's, even at a little over 1/10 of a watt, it's going crazy. And it's wiggling quite a bit. Now I'm going to vary the strobe just a little bit so you have an idea. And this is the same sort of strobe that you'll see in discos and that sort of thing. The cup isn't really changing. What we're looking at is changing. And the strobe frequency is just a slightly different from the frequency that we're actually driving the cup. Now if I touch the rim of the cup, that's with my fingernail, so that just shows you it really is moving. Almost the full width of the rim of the cup, which would be about 2 millimeters right here. This gets very loud in a few seconds. We're going to actually try and break it. So everybody, when I'm going to actually put the earmuffs on because I'm operating it, go ahead and feel free to plug your ears.
And you probably should. Just cover them right up like this.
Yeah, we're gonna try and break it right now. We'll see if we can do it.
They're over there.
Okay, I'm going to make sure I'm exactly tuned. Okay, we're pretty good right here. Okay, are you ready? 3, 2, 1. Whoa! These actually explode. They don't just fall apart, they blow up. That's why there's actually a blast shield on the front of this thing. We tuned the frequency to the exact frequency of the cup and then just increased our amplitude. And eventually the cup was no longer able to take the stress. How do we know what frequency to start with? Well, it's actually pretty easy. We ping the cup, just ping. I listen to it. We turn the signal generator till it's approximately the right frequency. We set it on the piezo pad and then just sweep past. It's very simple. When the cup goes into the resonance, you'll see almost no sine wave, and all of a sudden it goes, whoa, it just gets big. It gets enormous because of the coupling. So it's actually very easy to tune with this system. This is our cannon. And, well, there's some fun history behind this. You can see our cannon. It's a little pounder truck donated by my daughter. We mounted on the top of it a stainless steel barrel with a little spark plug on the top and a little holder, and we can adjust the angle. And we have a very simple way of actually firing it. And the principle that you can get a lot of physics out of this. There's just a ton of physics you can do. But the one thing that we're really looking at is action-reaction. And, you know, kind of for any action, there's an opposite and equal reaction. We have a little marker here. That just supposedly gives you a visual reference to where the little truck is at. And we have a power supply leading into our spark plug so that we can, I don't know if you all can hear that. There. A little spark goes off. We mix a combination of water and a chemical called calcium carbide that's used in miners' lamps, produces an explosive gas. Now this is going to go pretty quick, so if it works, well, it's hard to keep your eyes on two things. The ball's going to go that way. Watch out, you people over on the end over there.
Move over.
And hopefully, if it works properly, the truck will go this way. So use small scoop, not big scoop.
We tell them that.
Okay.
No, it
and
goes
the ball,
better.
the projectile is actually a tennis ball, so it's not too lethal. Okay, dump it in. You can see the gas. 3, 2, 1. Oh, well, kind of pathetic. We only got 6 inches.
Oh, wow.
Well, we tried. On this, we have action-reaction. Whenever you have something going one direction, pushing against something, there's an equal and opposite reaction. So the cart goes one way, and the ball goes another. We'll see this principle come out a little bit later when we talk about the V1. We're going to do a real quick optics experiment we just thought people would be interested in. See a great big flask of greenish. It looks like
mysterious.
It looks like something out of the brain of Morbius. But it's actually fluorescein in water, fairly innocuous. In fact, American pilots actually have a big packet of this. If they have to eject over the sea, the package is punctured, and it colors the entire region of sea where they're at with this bright green fluorescent color, and it's very easy for them to spot from the air. So we have this large flask, which simulates the eyeball itself, and in front of it there's a lens. We have a series of lenses. We have the normal uncorrected lens, which normally focuses it. Then we have several failed lenses, long focus for those of us who wear glasses, and then the correcting lens with it, and short focus with the correcting lens. And this is similar to something you'd see right out of a textbook. But what happens with the long focus is the focus of your lens is deformed enough, or your eyeball shape is deformed enough, so that the focus is actually behind the optic nerve. So your image is fuzzy, and it's not clear. With correction, it goes right to the back of the eye. With the short, it's focused somewhere inside of the eye itself instead of at the back of the eye. And with eyeglasses, the correction will drop it right up to where it's supposed to be at the back of the eye. I'll actually rotate it a little bit so everybody can see it. So there's the normal lens, and the focus occurs nearly at the back of the lens. In fact, it's pretty darn close. You can see how the beam expands. Now, if we put the short focal length lens, and again, I'll do a quick rotation on this so everybody can see. The focus actually occurs inside of the eyeball itself, so it's not quite right. If we put the eyeglasses on it, and this particular person has a long nose, so it actually has to go out here. You can see the focus then drops right down to the back of the eye. Long focus. We use our highly technical image plane here. You can see it's just a sheet of white paper. And the focus is right about here, where it gets as small as it can get. So it's actually outside of the eyeball again. Show that to everybody. And here's our eyeglasses. Brings it right up to the back of the eye. So this is actually a quartz crystal. So you have silicon dioxide arranged in a hexagonal form. And then if you squeeze it along appropriate crystal faces, you get a charge separation, which I've kind of drawn up here. And this is really for explanatory purposes. If you actually go into the crystallography of it, it's a lot more complex than this. But the basic idea is correct. When you compress the crystal, you get a charge separation. And you can take advantage of this charge separation in a number of ways. The old phonographs, which some of us will remember, actually used this kind of detector in the head. Later on, they went to magnetic for better frequency response. Our little piezo squeezer actually will put out about 10,000 volts. Well, this one has a crystal mounted in the inside, and when you squeeze the red handle, it proportionately compresses the crystal, just a tiny bit. And go ahead and switch to this camera, Mark. Thanks. And we've got an electroscope right here, and the electroscope, I'll briefly describe what that is. It measures voltage. There's a vane right here. Let's see if I can bounce it. I'm just bouncing it with my finger by vibration. And this vane is free to float. And the vane to the right of it, this really heavy one, can't move at all. But they're all connected electrically. So what happens, and a lot of people have seen this, when you have two charged objects and they have the same charge on them, they'll fly apart. So what happens on this electroscope is I'm going to put the piezo on the top of this and just squeeze it a little bit. Okay? That's about 1,000 volts right there. And this vane then is repelled from the main fixture. So there's a force between these two. It's just a way for us to measure the voltage easily. And it's even not very accurate for that, but it serves for our purposes. Coupled to this electroscope, it's a parallel plate capacitor. And some of you know what a capacitor is. For those of you who don't know what a capacitor is, it's very simple. You take two plates of metal and separate them. And in between them, something has to go there. It can be space, it can be air, it can be plastic. It has to have something in between them that's not conductive. So our parallel plate capacitor right here is movable. I can slide one plate in and out. And I'm going to hook it up to our electroscope. One side is movable. The other side is insulated from the whole base frame and this side of the plate. And in between, we can put a dielectric, which could be air, as it is right now, or I've got a big chunk of wood that's cut to just exactly fit. We'll slide it in there. So now we have a capacitor with a wood block as a dielectric. And dielectric just means an insulator. It's just keeping them separated. So if we put a charge on the electroscope, there's actually a large amount of charge on there right now. If I remove the dielectric, we'll see there's a huge amount of charge. You can make a capacitor with no dielectric in it, but it's cumbersome and you have to worry about it arcing and sparking. And if you have appropriate dielectrics, and wood isn't actually a very good dielectric, but it's really great for demonstrating the principle. There are some plastics and ceramics that actually make wonderful dielectrics, so you can actually place the capacitor plates very, very, very close together and not have them spark. So what a capacitor does then is it stores the electric charge. And once I put a charge on it, for instance, from the piezoelectric charger, it will continue to hold that charge until it's discharged. In this case, it's a very small amount of charge. So if I actually touch the capacitor plates, I can actually discharge it through myself, ka-ching. And I felt just a tiny little spark. So it's non-lethal. Some capacitors, like this one right here, has a metal cup that fits exactly into a beaker, on the outside of a beaker, and another metal cup that fits on the inside of the beaker. This is a form of a capacitor. It's called a Leyden jar. It was actually invented in Leyden, Germany, a long time back. And this little guy here will store enough energy to kill you. They're actually dangerous. And they're very simple to build. But it's a very powerful tool.
I'm innocent.
He's been trying to get rid of me. A lot of fun things you can do with them. Our current killer capacitor is in this great big Lexan box that you see back here. And in the box, you'll see 3 capacitors. And they're labeled 6.7 microfarads. I've simplified the entire system right here to a few things. We've got an electrical switch, a coil, and a capacitor. Initially, when we charge this up, we hook up a high voltage power supply and connect it across the capacitor. That will charge the capacitor up to whatever the potential is of our high voltage power supply. We remove the power supply, and then you throw the switch. And at the time that you throw the switch, the capacitor then only has one path that it can discharge in, travels through the switch, through the coil, and to the other plate. And this current typically with a capacitor is huge. It's enormous. These are special capacitors designed to discharge very rapidly. Mark, go ahead and charge that puppy up. So right now it's charging up. It's up to 2 kilovolts. We're going to take it up to 6 kilovolts right now.
We have 4 kilovolts. 5.
5
and a quarter.
6.
6.
Okay, Mark. Now Mark's just going to discharge it, and we're not going to do anything else except just discharge it. So give us a countdown, Mark.
It does get a little loud, so I'm going to cover up my ears.
So, oh, you don't have to cover your ears for this. But be aware, it will pop. 3, 2, 1, bang. Okay? And
later you have to cover
that's
your
just the energy of that set of capacitors discharging through a switch. So that was a spark, and we could hear the energy. If you're up close, you could see the switch actually spark. And so we're getting light energy, thermal energy, auditory energy, and as it turns out, there's also electromagnetic energy being propagated. But that's a lot harder to see. And most of the propagation of that energy comes out through this little coil right here. And on our model, Mark, point at the coil. And that little thing hanging out the front, can you rotate it around to the front? Yeah, there you go.
It says 4 turns.
4 turns, yes. The white plate hanging out the front has a coil in it that has 4 turns in it. Not a lot, but it's a big heavy wire. It's about as big around as the hammer's metal shaft right there. So it's a good heavy piece of wire. And that's embedded into epoxy resin with fiberglass to keep it from exploding. Okay, Mark. We've got an aluminum ring, just so it's non-magnetic, and we're going to lay it on top of the coil. And Mark's going to set the arm and charge it up to 6 kilovolts again.
I already said
Read it off, Mark. What do we got?
3. It's a little slower today. 4 kilovolts. 5. 5 and a half. 6.
6. Okay, Mark's going to discharge it again after a countdown, and I want you to keep your eyes on the ring. 3, 2, 1. Excellent. We managed. The electromagnetic field, when we discharged those capacitors, it actually created inside of the coil or inside of the ring, which we placed on the end of the coil, it acted as a transformer. So this would be the primary of your transformer, and the single ring, which flew up into the air, would be the other winding. And the force between those two caused it to fly apart. They fly apart from each other because both of them generate magnetic fields because of the time-varying magnetic field of the coil when we discharge it. Mark has a pop can, an empty one.
Warrens.
He's just going to place it on top of the coil again, and we're just going to launch a pop can just for the heck of it. Maybe you should roll it back a little bit, Mark. We don't want to kill a spectator. That's good. Go ahead. So Mark's charging it. And we're going to do our standard charge again, 6 kilovolts. What are we up to, Mark?
4. Always seems like it takes longer. 5. 5 and a half. 6.
Okay. Count down and fire, Mark.
3, 2, 1.
So same thing. It didn't matter if it was a ring or a plate of metal. It still works great. We're going to try one last thing with this, and it's actually kind of fun. He's going to take this pop can again, and instead of putting it on top, it happens that the hole here for our coil is exactly the size, by some strange miracle, exactly the same size as our pop can. So half of it is above the coil, and half of it is below the coil. And the question we always pose to our students then is, does it do nothing? because there's equal forces, or does it fly up again because that's what we saw the first time, or what happens? So Mark, go ahead and let's charge this up. Now this one you get to close your ears on. When Mark does the countdown, go ahead and plug your ears. And keep your eye on the can.
Just do the same thing. Okay, we're coming up on 5.
5.
We have to go all the way up to 11 here. 6. Well, you know, it's a show. It's coming up to 8 kilovolts.
That's why we have it in a big plastic case, too.
Yeah, there's a reason for this. 9. Now it's a little slower. It's pushing. We're up to 10, almost 10. 10. 10.2. I think he wants to stop there. Okay.
Okay, Mark's going to give a quick countdown.
Now you notice the technique that I'm using. So it's going to be loud. 3,
3, 2, 1. For those of you who could see, the can is actually hot and smoking. There's still some sugar left in the can, and it actually burned the sugar. There are many things happening all at once when this can collapsed and ripped itself in half. Again, all caused by an electromagnetic field that happened very, very quickly. And the forces on the can, both by the coil outside the can and the can itself, caused it to constrict and rip itself apart. This principle is actually used commercially to electroform certain metals to complex shapes that you couldn't otherwise form with a die. You can do it with a magnetic field because magnetic field doesn't care about going around corners. It will fill in the blanks. Okay, the Marx generator. There's my little history of the Marx generator. 1924, he came up with this idea. It's actually a very clever idea where you charge up a series of capacitors in parallel, and then by a very clever spark gap arrangement, discharge them in series. We hook up a power supply or a battery up to a set of capacitors, and they're all in parallel. So it charges them to whatever potential your battery is at. And once they come up to a certain charge, the very clever arrangement that Dr. Marx came up with is it automatically lines the capacitors up so that they're all in series. So if each one of these were 10 kilovolts, and they're like battery once they're charged, except it's not a chemical energy, it's an energy stored in the fields of the capacitor. So you stack them up, add them just like batteries. So just like a flashlight with 3D cells in it, you know, you have 4.5 volts. This stacks up, you add this up, and you have 50 kilovolts. And it's really kind of neat because it's arbitrary how large you can make it. If you start out with 10 kilovolts in each section and you have 10 sections, which is what our Marx generator here has, you actually wind up with 100,000 volts. And that's not insignificant because the capacitors actually store a lot of energy. So there's 2 stacks, and on each stack you'll notice a dull white and then a bright white, and they alternate. And the very bright white ones are actually capacitors. The dull white ones, every other one, are actually a nylon spacer. It's just a block. So on both sides, we have a stack of these. The other devices that you see are resistors. It's just and for those of you who don't know what a resistor is, it's just a kind of wire that dissipates energy, much like what happens in a toaster. It gets red hot when you run current through it. These limit the amount of current that can flow while we're actually charging the capacitors up. I'm going to go ahead and turn this thing on right now, and you'll just get to see what it does. And this just runs it up smoothly so that we can run it up to 10 kilovolts pretty easily. Made the people in the front jump. You saw the spark, and a quick judgment of whether a spark is dangerous is how loud is it. We have Van de Graaffs that will easily produce a 12-inch spark, but the amount of energy in that spark is not enough to kill you. This, even though it's a 4 or 5-inch spark, you could hear it snap. It made the front row down here jump. When it snaps, the amount of energy in that is actually only a couple joules, which is not a lot of energy by our energy standards, but it's easily enough to kill you. And so something like this is actually quite dangerous to run. Okay, next thing we've got is just a fun thing. We wanted to include this simply because it's something that any of you guys could build if you wanted to. It's very, very simple. What does it do? We'll tell you that first. It actually looks at magnetic fields, and it's very, very sensitive. It can look at a magnetic field that's very, very, very weak.
Okay.
Mark's aligning it right now. If you look at the dot on the wall over there, that's the output of our magnetometer right now. The construction is very simple. You've got a long glass plate. I'll move off to the side here. And we use super glue and two larger small glass plates, wedge a thin filament. And for that we used a Kevlar thread. We've also tried fiberglass. Probably regular thread would work also. It's best to get a thread that doesn't have twist in it so that it will just hang straight. And glued to the thread, on the back side of the thread near the glass plate, we've got a magnet. One of the very small, strong samarium cobalt magnets. You can buy them at Radio Shacks, like 50 cents for 3 of them. They're cheap. And to the front of that magnet, we glued a little chip of a first surface mirror. And so off the first surface mirror, we shine a laser beam. That bounces off, and you can see that laser beam echoed on the wall right there. And I was just leaning on the table. So that's another nice thing it actually does. Mark, stop banging.
I've got to be a troublemaker.
So it's sensitive to vibrations, too. We've also glued a penny. One of the old-fashioned pennies that's actually real copper instead of a laminate. And what the penny does is it damps down the movement, the twisting motion of the magnet and the mirror. If you don't put the penny on there, if I were to bump the table like this, it would take 10 minutes for it to stop oscillating. It would just continue oscillating it would make it impossible to read. But with the penny, it's a similar effect to when we fired the ring off of the killer capacitor. Whenever you have a changing magnetic field, it induces a current in any metal or that's nearby. And that current creates a magnetic field that damps. So what happens if this little magnet on the string twists, the magnetic field through the penny changes, and that causes it to damp. And it keeps it from vibrating. It will still move, but it doesn't oscillate. Go ahead and pick up a magnet over there, Mark. Mark's off the end of the bench. And that's actually a pretty weak magnet. It won't even hold itself up if you stick it onto an iron wall. And if you look at the dot on the wall over there, he went off scale.
I have to adjust it.
Go ahead and move back further away. We've actually measured some of these in our lab, and it can measure a standard hand magnet at 20 or 30 feet away. And it's just kind of a fun toy that's easy to build, and it's kind of neat. I have a friend who actually built one based on this model that has actually seen airplanes flying over. It perturbs the Earth's magnetic field enough that you can actually see it move. It's really pretty incredible. More induced currents. This one's kind of fun. This is a little experiment that we call the levitating ring. Very simple again. Everybody should remember their schematics. Switch. That one I didn't go over. I thought it was self-explanatory. You plug it into the wall. And you've got a coil, and in the center, you've got an iron core. In our case, this iron core is really brutal. Went down to the welding store and bought 4 or 5 pounds of welding rod, just 1/8-inch welding rod. And I actually made this dissectable so you can actually see inside of it. There's our iron core, and for those of you up close, you can see the windings. That's all there is to it. I mean, it's really simple. You have a coil, a switch, iron core. We have a PVC that we slide over the top just to make it neat and tidy. We like to be neat and tidy. Again, aluminum ring, and let me crank this up. It's really kind of cool. It's really kind of neat, and it's fun. If I hadn't popped the fuse in this so fast, you can actually, if you have a variac, you can actually vary the electric current in the coil and run this up and down, and it will just hover at whatever position. Now, if I turn it on and hold it on, I mean, it just hover there. And it really tosses it up. And again, this is what's happening is this coil is plugged directly into the AC mains, so it has 120 volts going through it. That's alternating current, so it's sinusoidal, and it's essentially going on and off at that frequency. And what happens is the magnetic field is captured and amplified to some extent by the iron core. It's confined to the iron core, and that's causing an induced current in the ring, and that current is making the ring make its own magnetic field. And so the ring is actually making its field because this field is changing. And when it does that, it's actually repelling. In fact, I could have one of you all hold this. I'm going to hold it down for just a few seconds, and it's already too hot to handle. And this is another principle which is really kind of neat. They actually make ovens based on this principle, and you could probably go down to Big George's and buy one of these puppies. They're real expensive. It's called an induction oven, and it requires special pans. I think they're just cast iron probably, but you put the pan on the top and the pan gets hot and nothing else. It's really kind of neat. They're expensive. I don't know how well they cook. I prefer fire myself. But it really gets hot and it works fast. Oh, just as a quick anecdote, here's a ring with a split in it. So it's actually got a cut out of it. Nothing happens. Because there's a cut in it, even though there's changing magnetic field in it, there's no complete circuit for the currents to flow. So the ring has to be complete so that the current can actually flow through the ring around in a circle. Ah, at last, we're to the Tesla coil. This is one that's dangerous, and anyone who has medical electronics, could you please, we have to hide them from the radio frequency field off of this. We have a variac, a step-up transformer. In this case, our step-up transformer steps up to about 8 kilovolts. 2 coils. These are, I labeled them here, RF feedback suppression choke coils. What that does is there's such high voltage developed on the business side of the Tesla coil that it can feed back into the transformer, the step-up transformer. And the step-up transformer isn't made for those high voltages. It's only made for 8 to 10 kilovolts, and if it gets more than that, it will actually burn up. It will short out. So these prevent those high voltage spikes from going backwards. Our primary side is this flat spiral coil on the very bottom. The long skinny coil, that's the secondary. This is this one right here. The toroid's on the top, pretty easy to see. So in essence, the Tesla coil is a very, very simple device. Only a few necessary components. And the elegant thing about this device is that this switch right here, it's a spark gap switch. When that sparks, it discharges the capacitor, which has been charged up by our power supply. And when it discharges, through this primary coil, the big fat one on the bottom, it rings like a bell, like a tuning fork, but electromagnetically. And what happens is the other coil that's on the inside of it, the long skinny one we call the secondary, that one is tuned just like the tuning forks, similar, so that the big primary coil is tuned to the secondary. So when one rings, it rings the other. And we have a bunch of effects are happening all at once. These are coupled both magnetically, electromagnetically, and by tuning them so that their frequencies match. And wonderful thing happens, and Tesla was a genius to discover it. It actually multiplies by harmonics then, and you get these huge, enormous voltages. This probe right here is just a grounded discharge probe. The discharge probe goes right to ground, and I'm just going to draw a power arc so that you can actually see it when I get to this. One of the nice features of this, which is why we had a couple people actually leave the auditorium if they're wearing medical electronics. This produces so much radio frequency transmission that it could be dangerous for that sort of thing. See, I'm this far away, and it takes a little over 1,000 volts to fire this tube. So the field right here, and this is barely running. So you can imagine the field when we actually run it full out. The propagation from this is just enormous. Go ahead and run it up to 60. Go ahead. Okay, that was just simply a grounded discharge. No big deal.
Watch this.
Now this is the fun.
I don't do this.
Now, to date, I've only managed to talk 2 professors into doing this. And I think actually both of them are in here, but I won't point them out. Most of the professors are not brave enough to do this. This is a solid aluminum rod, okay? Now, you can draw a spark to the output of this, so long as you don't develop a power arc and you're highly insulated from the ground. We have back here a stool, which just a polyethylene bucket with a stand marked on it. I'm going to stand on this, and that insulates me far enough from the ground so that if I'm drawing an arc to myself and I become charged with the same potential as the globe, that it doesn't arc through my shoes, well, from my heel, through my shoe, through the rubber floor, into the cement, into the earth. It burns little holes in your feet that really hurt. Okay, you ready, Mark? Go ahead and do 1 to 1. All the way, 1 to 1. Now, I could feel that tingle, but it doesn't hurt. This is operating at about 500 kilohertz, so there's other interesting physics going on that cause the high-frequency currents to actually travel over your skin. So it doesn't actually penetrate into the inside of your body. One last thing with this, which is kind of fun. This is an 8-foot fluorescent that we stole out of the back lab. Go ahead, Mark, fire that baby up.
Can you smell ozone?
Well, we saved this for last for a number of reasons. It ties together a whole bunch of principles that we've covered earlier. And once we touch it off, a lot of you, if anyone's sensitive to fumes, you could stay long enough to watch it run, and then you want to evacuate. Even though it will actually run for only 20 or 30 seconds, it makes a significant amount of fumes, which may bother some people. The pulse jet consists of just a long resonating chamber. So here's the main chamber. It's just a very thin tube, and it has a particular frequency that it operates, just like the hoot tube that we showed you. It has a self-resonant frequency based on its length and its construction details. The igniter is just a standard little model spark plug. This front section contains the intake manifold and a carburetor. The carburetor is really, really primitive, but it works. It's one of those devices that the Germans built, for those of you who don't know. It's actually a V1, which was called the buzz bomb. That's what this was based on. And the carburetor is actually just a long rod with a hole drilled for the fuel intake and a tiny venturi with the air injector right there. Once the fuel starts flowing and the engine starts operating, you actually don't need air injection to keep it running. The shape of the intake manifold actually structures the air so that it continues to feed mixed fuel into the chamber. It has one moving part, which makes it really elegant. This is the inside of the manifold. There's a set of flapper valves, and I've drawn them as little circles here. And they cover up a set of holes, 10 holes, that are drilled at an angle. And the flapper valve is just a spring valve that sits down. And when you inject air into the front end of this, the valve lifts up. And when it lifts up, it lets in a little bit of air and a little bit of fuel. When the fuel mixes in the chamber, the spark plug ignites it and it explodes. When it explodes, it exhausts out the back. Now this happens at a particular frequency based on the details of the tuned chamber and of the little springs, the flapper valves. I'll take the carburetor out of this so you can just see how small it really is. Just a tiny, tiny little device. These were actually sold, I think they were called Dynajets, and they're sold as models to put in little model jets. The jets would actually get up to over 200 miles per hour. So they're a real bear to fly. It's easy to lose your plane, you know. I mean, it's gone before you can see where it's been. The Germans actually used acetylene to run it. It will run on gasoline, fuel oil, kerosene. We actually use lighter fluid. It will run on virtually anything that you can atomize and will burn. We actually have it mounted to the cart and it's clamped down and the wheels are actually locked. We tried running this once and I actually started walking the cart across the lecture hall. So we do a quick preheat. I'll preheat the engine chamber we have just a little propane cylinder. That warms it up so that the initial firing of it occurs easily. The fuel chamber, I'm going to go ahead and fuel it right now, is the little silver globe in the front. So we put in about 30 milliliters of fuel into the little spherical gas tank. I warned you about the noise. The lights are dim. We have a whole check-off list here because it's just like running an aircraft. So I hope you all enjoyed it. Hope you have a good week. Thank you, Mark.
Saturday Morning Physics is sponsored by the University of Michigan Department of Physics and by gifts from friends of the program. Local broadcast is made possible by Pfizer Incorporated.